Hello students, the last topic for this semester is algorithm analysis and complexity, and I am presuming that you have watched the video that was posted in the required videos section, which was a Building Java Programs chapter 13 complexity video, which is about 17 minutes, but it's worth every minute because it goes over the foundations of how you calculate runtime complexity. Now, what I would like to do today is I would like to go over our big O notation worksheet that's been posted and also go over two items. One is from Practice It, the problems on Practice It, and also go over some of the problems in Code++, which have the links for those problems are in your exam 4 prep. I would suggest, firstly, go ahead, watch the complexity video from Building Java Programs. The links is in this module. Secondly, go over exam 4 prep, which tells you what are the topics in big O notation that you need to review. And now let's go to the big O notation worksheet so that we can work our way through some of the problems, then move on over to Practice It and then code step by step. And that will be, I think, a lot of good preparation for you. I'd also like to point your attention to a data structures prep notes that I have prepared. And this is a kind of a cheat sheet, if you will, to let you know what the solutions are for the operations in these particular data structures with regard to complexity. All right, so let's get started with the big O notation worksheet. Actually, I might just want to download that and then. Yeah, so if we've watched the video, we know that the way to calculate complexity is firstly check and see how many statements are actually going to be run. Then we work on the presumption that each statement, no matter which type of statement it is, it'll take exactly the same runtime. So if there's one statement, let's just presume that's 1 unit of time. And if there's n statements, then we're going to say it's n units of time. Our task in calculating, in determining the complexity is to see what happens to this algorithm as n grows, i.e., what is the runtime versus the growth rate. And as we know, n is the amount of data that's being processed. It could be, an array of n elements. It could be just a single data piece that's getting processed like a zillion times. And we need to know how much time it's going to take. At this point, we are not worried. In this particular piece of our course, we're not going to worry about the space complexity, but that could be a consideration in your future courses. I would also suggest reading the section 13.2, which gives amazing tables which compare what happens when you choose a good algorithm and how you end up with a nice complexity, and also what could happen if we are not careful with choosing the correct algorithm, because that could give us a horrible runtime, and that in the practical business industry, it's not acceptable that we wait for 55 minutes for our program to execute and give the answer. So I, again, watch the video, read the textbook section, and then we are here now to do our work. Now let's go to the sample problems here. It says, how many times does each box statement get executed, and what is the big O notation running time of each method? Now, as you know from your readings, that the big O notation is calculated by determining how many times is this how many times is this data going to get processed. And sometimes we end up with a number that looks like, oh, this is going to get executed n squared plus n divided by 2 plus 3 or 32, let's say. Then the big O is going to tell us that as our n grows towards infinity, as our n becomes very large, then we don't need to worry about this constant here, and we don't even need to worry about this half here. The coefficients don't matter. And in fact, as n tends towards infinity, n doesn't matter because the chief player is going to be n squared. And therefore, so in the exams as well, I will not expect you to come up with precise functions like this, but I will just expect you to say, oh, this is of the order n squared, and this is what the big O notation, this is n squared. And this is what, the big O means. So let's look at problem number 1. The solutions are given at the bottom of the page, but nevertheless, let's work through this. Now we've got an integer array that's coming in. Now we can presume when we are given something like this that the length of the array is going to be n, right? So what we're saying is I is equal to 0, I less than n. Now this statement is going to get executed one time because that's how the loop works. This test is going to get executed n plus 1 times, n times inside the loop and 1 time to exit from the loop. And then this one is also going to get executed. This one is going to get executed n times. Now, that plus this statement is going to get executed n times. So we have with us 1 plus n plus 1 for this plus n plus n, right? So this looks like to us, when we add up all of these numbers, we get, oh, this looks like 3n plus 2. And the runtime then is going to be 3n. If we assume 1 unit of time, it's going to be 3n plus 2. Then using the simplification that we need to do, we are going to remove the coefficient, remove 2, and then we are going to say, oh, this is of the order n. Right? And that is going to be the correct answer, because if we move down, we see it gets executed, and therefore this is of the order n. Now let's look at the second problem. Now we know that any time we have a nested loop, then we have to be a little bit careful to check and see if you're going to get a quadratic equation or what's happening here. That may not be true all the time, but sometimes it is true. So here, this is n, array length is n, and then this is another array length, the same array length, so that's n. So I is equal to 0, I less than n. This is going, the outer loop is going to get executed n times, and each time, for each rotation, if you will, of the outer loop, the inner loop is going to get executed n times. So n times n makes it n squared, and therefore this is an n squared algorithm. As you can see, I have stopped worrying about dissecting the for loop, and I'm just, apart from just an examination to see if there's any tricks inside this loop, I'm straight away coming down to see how many times this internal statement inside the nested loops is going to get executed. And that's n squared, because we know by now how to do the simplification. Now let's look at this one. This one, the outer loop is going n times. And then we see, oh, there's a nested loop. It's very easy to quickly to jump to conclusions and say, oh, this is n, but it's not. You see, j is less than 10. So this looks like the inner loop is going to get executed 10 times. The outer loop is going to get executed n times. And therefore, this is actually 10n. So this statement is going to get executed 10n times. And we know if we drop the coefficient, it's going to be just order of n. And let's check our answers here. For our answer was n squared for 2, and then it is n for 3. And so we have 2 more problems to go through. And here, again, if we look at problem number 4, we see this is n. And then this, it doesn't seem to start with 0. It starts with I, but it goes up to n, which tells us that n times what's happening is that this is likely when I is equal to 0, this is going to be 0. When I is equal to 1, this is going to be 1. When I is equal to 2, this is going to be 2. And all the way through, it's going to go up to n minus 1. Right? Because this is going to be at n minus 1, when I is n minus 1, this is going to be n minus 1, right? And then it will get executed 0 times. So basically what's going to happen is I've reversed this order, but this is the number of times it's going to get executed is correct. The reason I wrote this is because it's easier for us to come up with the sum of the sequence of numbers. It's n plus 1. This will be n times n minus 1 over 2. And this will be, so this part is actually of the order of n over 2. And when you multiply n times n over 2, you get n squared over 2. And we know that coefficients don't matter, so we're going to disregard this. And it still works out to be an n squared algorithm. So let's check if our answer is correct. So this is n squared. Now, know that I'm not expecting you to know the sum of the arithmetic sequence or sum of the geometric sequence, but it is enough for us to know that regardless of whether j starts with 0 or it starts with I, then it's going to be an n squared algorithm, because eventually this, even if it gets executed n over 2 times, that is still counted as an order of n squared. Now let's look at this one. Here, the reason why we need to look carefully at the loop is because now we have I is equal to 1, I is less than equal to n, and then I is equal to I times 2 here. So the loop increment can be set up in a way that your loop actually does not execute n times, but it could either execute more than 10 or less than 10. It could also execute 0 times. It could also execute an infinite amount of times. And it is this increment that may control how many times your loop is executing. So if you look at this and we say, oh, let the number of pieces be equal to 8, right? If it's equal to 8, then the first time I is equal to 1. Then the second time I has become 2. Then I becomes 3. Then I becomes 4. Right? And then I is still less than equal to n, which is 8. I becomes 8. So the first time I is equal to 1, right? And then second time I becomes 2. The third time I becomes 4, because it's getting multiplied by 2 every time. And then it becomes 8. At the fourth iteration, it becomes 8. And then the last time it becomes 10, and that's when it exits the loop. So basically it looks like this loop is going to get executed 4 times, right? So 1, 2, 4, and 8, right? So this has become 4 times. Now let's take, so this is the loop is getting executed 4 times. Now if it is, let's say 4, then it gets executed 1, and then I becomes 2, and then I becomes 4, and then I becomes 8, and that's when it exits the loop. So this is going to be equal to it's executing 3 times. When we have 2, it executes the first time, and then it executes I becomes 2, and then when I becomes 4, it comes out of the loop. And when I is equal to 1, then it executes 1 time. And when I is equal to 16, when n is equal to 16, it executes 1, 2, 4, 8, 16, and at 32 it comes out. So this is 5. So we are seeing a pattern that 1 raised to 0 is 1, 2 raised to 0 is 2 raised to 1 is 2. So it looks like if we have log to the base n, where this is our n, And we know that log to the base of 4 to the, and if we take the base 2, that is going to be equal to 2, right? But we are getting 3 here. That's fine. So, and here, log to the base 2 of 8 is actually 3, but we get 4 here. So there is a 1 plus adjustment or correction that needs to be done. But nevertheless, this looks like this algorithm is log to the base n of 2 plus 1, right? Because log to the base 2 of 1 is actually 0, and then we've added 1. Log to the base 2 of 2 is 1, and then we've added 1. We've got 2, and so on. But we know that the plus 1 is inconsequential. We can remove this, and we can say that this is actually a log to the base 2 of n algorithm. So that is something that we need to watch out for, that when we have a loop, we need to examine before jumping into conclusions. It could be a constant time loop, or it could be a log loop, or it could actually generate an infinite loop. So just to double check the answer, exactly log n plus 1 times, and therefore this is of the order log n. Now I'd like to move quickly to our practice set problems and go over this problem. So here we say for I is equal to 1, I less than equal to n, I plus plus, and j is equal to 1, the inner loop is a constant loop. And because it's a constant loop, only the outer loop is coming into play, and therefore it's of the order n, because this n represents the n pieces of data, and that's how many we've got here, right? All right. The second problem is what happens, I think I started with the last problem. So let me go back to the first problem. Now, if you look at this loop is executing n times, but we also have, if j is an even number, then increment this. It doesn't matter. This is going to get executed n times. This may get executed, if all the numbers are even, another n times. But that doesn't matter, because we know we can drop the coefficients. The real thing is that this get executed approximately n times, and that's the correct answer. Let's move on to the next one. Here we have 2 for loops, but they're not nested. They're one after the other. But the first one in itself is nested. So we are going to say I is equal to 1, I less than equal to 2n. So this is 2n, right? It's not n squared, it's 2n. And then the inner loop is going to get executed n times. So n times n makes it n squared, order n squared, plus there's another statement that's getting executed approximately 200 times. But this is a constant which gets dropped off in our simplification, and we are left with an n squared, and that is the answer right here. And then here, so the answers are right here, and these are the correct answers. So now let's look at this one. This outer loop executes n times. The inner loop, as we know, j less than equal to I, j plus equal to 2. So j is incrementing in steps of 2. But even if it's incrementing in steps of 2, it is ultimately going to evaluate to the order of n, because it starts with I and then it goes all the way up to, and because I goes all the way up to n, at some point j is also going to go all the way up to n, and then all of those lesser numbers which get, when we do the sum of the sequence, this is like a sum of the sequence problem, it evaluates to the order of n, and this will become an n square problem, and this is a constant thing. So here is our answer, that it is an n square problem. And then the last one is n, and I think we're done with the big O. I'd like to go to the code step-by-step problems. There is an important problem here which relates to array lists, and for that I'm going to ask you to watch your video really carefully, which explains why the table for some of the more complicated data structures like array lists, maps, sets. All of that is something that we need to think a little more deeply about. But let's do these problems. Now here we've got, these are the problems that you're meant to practice as part of your exam prep, and the links to this are right there in your exam prep document. Now I is equal to 1, I less than equal to n plus 2. So this is to the order of n. This is also to the order of n. So the answer is of the order of n. Now let's look at this one. Outer loop n minus 5, inner loop n minus 5. So both of them are to the order of n. So this answer here right to the right is n squared. The third one, the outer loop is going only up to 1,000,000. 1,000,000 is still not a big number. When you see a constant here, don't worry about the value. It could be 1, it could be half, it could be 100, but it turns out that it is 1,000,000. But even that is not of the order of n. Any constant is completely okay. And this one, I is equal to 1, j less than equal to I, we know that there's a maximum limit, and this is only 1,000,000. So this is a constant loop. This one again is a constant loop because again, j less than equal to I here, j less than equal to I, and I is bounded by this number. So the answer is order of 1. And now this is an interesting problem, the array list problem, and you may see a problem like this in your exam. Remember that an array list is like an array, but unlike in an array, you can actually insert an element inside the array list. And when you insert an element, you end up scooting all of the rest of the elements to the right. And if you delete an element, then you actually have to scoot up all the elements from the left, right? So if we insert an element, then all the elements to the are going to get right adjusted, and if we delete, all the elements are going to get left adjusted. Now, you can add an element at the back of the array list because it works like an array in that sense, but removing an element, adding an element at a certain position, which is like insert, is going to cost you n, order of n. So let's look at this problem. Here this says list.add for I is equal to 1, I less than n squared. Outer loop is doing n squared, inner loop is doing n, so which totally means n cubed. But what about this statement, this array list statement? Is it an add at a particular position or add at the back? Now I see that this is add at the back, so I can tentatively say, oh, this looks like an n cube, and then come and examine this one, which says this is 2n, so the order of n. List.remove, so when we remove, we know that this is an order of n. N times n is equal to n squared, but that's overshadowed by the n cubed in the first part of the problem, and therefore we will stay with order of n cubed, and that is the correct answer. Now, with hash set and tree set, if a hash set is implemented as a table, then we know that if you want to add an element, that's just order of 1. But we're given a tree set here, and a tree set works like a binary tree, and therefore this works n times to remove and add. Remove and add operation is a log n operation, and if you do that n times, it's going to be n log n. But for the exam, you wouldn't need to worry about tree sets because we haven't done that. We will only keep ourselves to the only data structure that we will consider is an array list. So with that, I'm going to stop the overview for algorithm complexity and big O notation.